graph visualization using ZigZag persistence.
Thank you for the introduction. So my name is Claudio. I come from Linnaeus University in Sweden. And today I want to talk to you about ZigZagNetVis. So this work is heavily based on the concept of network and graphs, and here we are working with the definition of a set of nodes and edges. But the thing here is we are working with a specific type of graphs, so we are kind of dealing with the idea of temporal graphs. But what is the problem that we want to solve exactly? It's the idea of the scalability. So, and of course, when we talk about scalability, there are several different things, right? Can be the node, can be the edges, can be the time. But for the sake of this work, we are more focused on the time idea. So, how does it usually look like common network visualization, common temporal network visualization? First of all, timeline is one of the most common things. So this will be a common representation. So what happens when you increase the amount of timestamps? This is what happens, right? It increases the layout horizontally. Another common technique to visualize temporal networks will be a node link diagram, right? An animated node link diagram. And then the time will be impacted by the duration of the animation. So you may think like, okay, there are easy solutions to that, right? In the timeline thing, we could just group up more the edges, right? And then we'll end up saving more space to put even more edges. Or for the animation, why don't we just speed up the animation, right? And then we'll end up solving the problem. But the thing is, these solutions are not necessarily good enough. Because of course, if you keep compressing the edges, you end up not having space anyway, if you have too many timestamps. And when you have the animation running too fast, it's just edges blinking, so you cannot actually see much. So for that, we are working with the concept of resolutions. So imagine this is the original resolution of the network. So what happens when you start increasing the resolution is like you start grouping up the edges, right? So let's say resolution 2, then in resolution 4 you pile up the edges until you reach a point where you actually have all the edges in a single timestamp, which we actually don't want, right? Because then we end up coming back to the static graph. So given that we have multiple resolutions that we can have that presents different patterns and different things, how do we actually choose a resolution that is meaningful and has some patterns that we can analyze? And for that, it comes our solution, right? So the ZigZagNetVis. So first of all, one of our first goals is to automatically recommend different resolutions, and also we propose visualization for you to be able to see what happened inside each resolution. So for the recommendation of resolutions, we work with concepts of topological data analysis, TDA. I will not get into the details because it's so many things, but for the sake of time, I will just briefly explain to you how does they fit in our methodology. So first of all, we have the graphs, right? The temporal graphs. So we have this defined by the timestamps. So the first thing that we do is we calculate the time slices. We just group them for different time slices. Then we start applying the zigzag filtration. What is that? What does that mean? It means that we are doing the union of the graphs, which will give us the merges and splits of that. So how would we do that? So let's say G0 and G1, the union of that, we just have this representation, and we keep doing that for all the other graphs, G1, G2, and so on. With that, we have the persistence homology, which is a set of features. For the sake of this work, we are just interested in the 8.0, which gives us the number of connected components. And with these connected components, we end up calculating and having the barcodes, which is basically seeing the connected components over time. So we start with 2 barcodes, then eventually we go to 1 barcode because we only have 1 connected component. Then this keeps stable until the last timestamp when we still have 2 more. So the thing is, given a barcode that we have for let's say 1 resolution, we take a second resolution and we see what changes between these resolutions. So imagine that these red lines, these red bars here, that these 2 red bars in resolution 1 will end up merging in the second resolution. So with that, we calculate the bottleneck distance, which as when the value of the bottleneck distance is higher, you have a bigger difference. And then we do that for consecutive resolutions. So we calculate for every consecutive resolution. With that, of course, we will have different values here. Then we define a threshold mathematically. So what is above that threshold, it means that there were more changes in the graph. So we kind of suggest those resolutions to the user. So let's say in this example, we end up suggesting resolutions 2, 4, and 8. So getting back to the concepts of the barcode, just to show how do we plan our visualization, which is quite straightforward because we just did a colored version of these barcodes to visualize the connected components. So imagine that we have these classes here. So we will have something like that. The bars mapped by the which based on the number of nodes and the colors over time as well. This is how it looks like in a real world scenario. This is a version of our system running. So as you can see, of course, the system is highly interactive. We can see one resolution at a time. We see the flows, or we keep switching that for different selections and so on. So in here we have a case study for a primary school network. This is basically a network of people interacting between themselves with the students interacting and the teachers. So this is the bottleneck distance, the resulting of that data set. So what we have here is we have 5 different recommended resolutions, and in here I'd like to show you first the resolution 6. So this is how it will look like. So you see, like, there's a lot of connected components and a lot of information, right? So because it's just a small resolution. So what changed from, because one of the recommended resolutions is actually resolution 8. So what changed? So these 2 large connected components, they end up merging to resolution 8. So it's here in the bottom. So that was a big change on the graph. So this is why resolution 8 is one of the recommended resolutions. But it's kind of hard to get patterns here, right? It's too many things, too much information. So look what happens when we have a much higher resolution. So this is with 76, one of the other recommended resolutions. So in here you have the pattern is much more clear, right? So for instance, we can see students in their respective classrooms in the beginning of the network. We can see that something was happening in between. So we see a merge of students at some points. And even in the middle here, we have what we assume it's like a lunch break, where basically everyone groups up in the central part of the network. Jumping to limitations, but also possibilities for opportunity. We didn't necessarily compare the resolutions side by side, but that is something that we could do in the future. And also the running time for these resolutions can be high depending on how many resolutions we compute and we compare, because we need to run the whole process for every single resolution. But that's it. Thank you very much.
Thank you. Questions?